Hello students. When you hear such words like resistance, voltage, resistivity, or Ohm's law, or perhaps something like electromotive force, potential difference, these are terms associated to electricity. Alright, so when we discuss electricity, we are referring to charges in motion. Okay? In the last video or tutorials, we already tackled concepts related to electrostatics. So this time, we'll be focusing on basic direct current circuits. Our first example has to do with a source in an open circuit, such as the one in the illustration or circuit diagram, which shows a battery, with a maximum potential difference, also known as electromotive force, or shortcut term is EMF, denoted by a Greek letter epsilon, equals 12 volts. So this battery also has an internal resistance, denoted by small letter R, amounting to 2 ohms. Notice that there are loose wires to the left of point A here and to the right of point B, all right, or to the right of the ammeter, I should say. They are not connected to anything. So you are asked to determine the ammeter reading and the voltmeter reading. Both instruments are commonly used in measuring voltage and current respectively, and they are assumed to be idealized. All right. So if you notice, the symbol for a voltmeter is just a what do you call this? A circular or a circle which has the capital letter V in it, while for an ammeter we have the capital letter A, representing what we call an ammeter, and for the voltmeter we have V stands for voltmeter. So our question is, what would you think will be the current reading or the ammeter reading and also the voltmeter reading? It's the voltage across the battery that's being measured by a voltmeter, and then the ammeter also measures the current that passes through the given point in the circuit. So our answer to these questions is that for the voltmeter, it should read 12 volts, while the ammeter reading will just be 0, as there is no current here in this part of the circuit. It is because both wires to the left of point A and the one to the right of ammeter is not connected to any what we call load. All right, and therefore that means there is no current passing through the ammeter, so it's not reading anything at all. And because of that, the potential difference, across point A and point B, which is also the voltage of the battery, we'll just be measuring, the maximum possible electromotive force, which is already given as 12 volts. Proof to that is based on the formula for determining what we call the terminal voltage, labeled base of AB. Okay, that is the voltage measured across points A and B. And that has, or that is equal to EMF minus the product of the current times the internal resistance, all right, small r. But the fact that there is no current, okay, there is no current passing through this uh, internal resistance R, that makes that equal to zero. All right, the current is equal to zero, and therefore the terminal voltage of the battery will just simply be equal to its electromotive force or EMF, and that is equal to 12 volts. All right, so we take note that the product of the current and the internal resistance is equal to zero. So this is an example of a source in an open circuit. An open circuit simply means that there is no complete path for current to move around from the positive terminal of the battery, okay, to the negative terminal, passing through the different resistances, if there are. All right, there is no such complete path, okay, that would provide supposedly uh, current passing through the whole circuit. So it is called, therefore, an open circuit. Before we proceed to example number 2, I just have one thing to emphasize in this circuit. I mentioned earlier that there is no current that will what we call flow. All right, there is no continuous flow of charge from the positive terminal of the battery, okay, to the negative terminal, okay. But you might ask, isn't this connected to each other, the positive terminal and the negative terminal, because of the presence of this wire? All right, could that wiring not possibly allow current to pass through? Okay, you might be wondering, why do you say that it is still considered an open circuit, okay, in spite of the fact that there is a wire connecting point A and point B? The answer to that is a voltmeter is an instrument that is designed, all right? It is so designed to have what we call an infinite amount of resistance, all right? Its resistance is extremely high. That's how voltmeters are usually designed. Now, assuming there is current that will flow from the positive terminal of the battery, okay, through point A and then passing through the voltmeter. But the fact that the voltmeter has a very high resistance, okay, when you say resistance, it is the ability of that particular component in the circuit to oppose the flow of charges. Okay, so charges may not or will not be able to pass through, okay, and complete its motion from the positive terminal to the negative terminal. Okay, so that is the nature and property of a voltmeter. If a voltmeter is so designed to have an infinite amount of resistance, an ammeter, on the other hand, is designed to have an almost zero resistance. All right? That is why an ammeter, normally an ammeter must be connected in series with the point where you would like to measure the current. Because whatever current passes through, for example, point B, will also be the current passing through that ammeter. And the voltmeter, since it has a high resistance load, okay, current cannot pass through it, and therefore, uh, if ever there is a current, the current will just simply pass through, uh, for example, in this case, it will just pass through point A to point B, all right? But not from A uh, through the voltmeter and then uh, move on to B and to the negative terminal. That's not going to happen because of the very high resistance of a voltmeter, all right? So the proper way of using the voltmeter and the ammeter should be such that the voltmeter should always be connected parallel or across any device, any resistor whose voltage you want to measure. Whereas the ammeter is connected in series with the point in the circuit where you are measuring the current. Our example number 2 is about a source in a complete circuit. Earlier, we talked about, okay, an open circuit. Now, let's look at the same source, okay, the same source that we uh, analyzed in example number 1, the same battery. But this time, there is a complete circuit, okay? So, using the battery example 1, we add a 4 ohm resistor to form the complete circuit shown in the diagram. Here is the 4 ohm resistor, external resistor that's connected, all right, here. And we're asked, what are the voltmeter and ammeter readings this time? Now that we have an external resistance, capital R, which is equal to 4 ohms. Okay? So, what do you think will be the ammeter, or what will be the current that will be measured by the ammeter, and what will be the voltage that will be uh, taken by this voltmeter? So, what's our first answer? All right. Again, using this formula for determining the current, okay, in this part of the circuit. For example, what is the current from point A around this, passing through the big R, passing through the ammeter, and then directly going into the negative terminal of the battery. All right, as indicated by this arrow that symbolizes the flow of positive charge, which incidentally is what we call conventional flow of current. Okay, and the conventional flow of current is always from the positive terminal of a battery, passing through the external loads, and then back to the negative terminal of the battery. Okay, let me add also something that's very important. All right, I hope you have already watched my tutorial video or video tutorial about electric potential. All right. Uh, this positive and negative terminals of a battery symbolize 2 points with different what we call electric potential. Okay. So the positive is considered to be of higher electric potential compared to the negative terminal. When you say 12 volts, an EMF of 12 volts simply means that the positive terminal has 12 volts of electric potential higher than that of the negative terminal. All right. So Why the choice of conventional flow of charge? Why is it from positive to negative? Because we say that uh, what is moving around the circuit, we imagine are positive charges. All right. So we use the basic rule that positive charges do repel. So we can imagine also that the high potential end of the battery, all right, the positive terminal, repel or repels the positive charges and force them to move around in a counterclockwise direction, right? Now, the fact is, it is the electric field that is established as soon as there is a complete path in the circuit, as soon as there is a path for current to move around. We also say that there is, okay, an instant electric field. Okay, there is an instant electric field in this conducting wire, and it is the electric field that actually is responsible for example, for transmitting the energy, electrical energy, okay, around the circuit, such, for example, the uh, the resistor is a bulb, okay. The electrical energy that is carried by the electric field, all right, will in fact be converted into light. The electrical energy, okay, carried by the electric field will be transformed into what we call light energy, and hence the bulb glows. Okay, so electricity, in other words, okay, is the root cause for what we call transformation of one form of energy to a more useful form of energy, such as light, okay, heat, or even sound. So that is what we mean by current moving around a circuit. Okay, it is not the current that carries the energy, right? It is not the current, or it's not the positive charges, neither the negative charges. Okay, they do not carry the energy, or they do not transmit the energy. Okay, so I mentioned about the conventional flow of current, which is from positive to the negative terminal, all right, passing through the external loads. There is also an opposite um, choice for the flow of charge, and this is what we call the electron flow. The electron flow, okay, is such that the current is represented by the flow of electrons, okay, electrons which are repelled by the negative terminal. So the electrons will drift, that's the right term, will drift through this uh, conducting wire, all right. So we imagine the wire to have what we call uh, loosely bound electrons, loosely bound free electrons, and these free electrons are the ones that are flowing or moving around the circuit. So in most textbooks, what is followed by most textbooks is the conventional flow of charges, which is from positive terminal of the battery to the negative terminal of the battery. By the way, we are not saying that from positive directly going into the negative terminal. That doesn't happen. All right? That doesn't happen because this very small distance that separates the positive terminal and the negative terminal, all right, uh, is something that charges cannot just cross. All right? So you might think, why not just go straight directly from the positive to the negative terminal. Okay? It is because, as I mentioned earlier, this positive terminal has a higher potential compared to the negative terminal. All right? And when you say charges, they don't just move through something that is not a good conductor. All right? Air is considered a poor conductor. So these charges, okay, are just or they just flow through a material that conducts electricity, a very good conductor such as a copper wire. So no way for them to be able to just go directly from the positive terminal to the negative terminal without having to pass through all the external loads, because the long path that they have to take, okay, is what is more convenient, right, for these charges to move around and complete their journey. I hope that is clear. Now, um, we will now analyze and answer the questions. Okay, in the presence of the external resistor amounting to 4 ohms, all right, we now have two R's, the small r and the big R. And how do we determine the voltmeter and the ammeter reading now? So according to our solution here, okay, the formula that we are going to use is the formula for finding the current, capital I, which is equal to the amount of EMF divided by the sum of the two resistances, the big R plus the small r. And when we substitute, the EMF of 12 volts to be divided by the sum of 4 ohms and 2 ohms. Okay, so 12 volts divided by 6 ohms will give us 2 amperes. And that is exactly the current that will be moving through this path. Okay, from point A, passing through uh, the external resistor or big R, and then the same current will pass through the ammeter. That's why, okay, that current of 2 amperes will be the ammeter reading. Okay, because it is the ammeter, okay, which has zero resistance. All the current that passes through it, okay, can be detected by the ammeter, okay, because of its practically zero resistance. Now, how about the voltage as measured by the voltmeter? So, we refer to that as the voltage across point A and point B, which incidentally is also equal to the voltage across the big R, okay, or the voltage across points A prime and B prime. So label the equality of the two voltages. V sub AB is equal to V sub A prime B prime. Okay, and using that what we call Ohm's law equation. I'm sure you are familiar with Ohm's law, which says that voltage is just equal to the product of the current and the resistance. So the current is 2 amperes multiplied by 4 ohms, which is the resistance of the big R. We get 8 volts as the voltage across points A prime and B prime, which just mentioned earlier is also equal to the voltage across point A and point B, and therefore that voltage is what is measured by the voltmeter. Our example number 3, which talks about how voltmeters and ammeters must be used. The voltmeter and ammeter in example 2 are moved to different positions in the circuit. What are the voltmeter and ammeter readings in the situation shown in this figure? Okay, figure A, and figure B. So notice that the voltmeter has been transferred. Okay, earlier it was connected across point A and B. Now it is transferred across point A prime and B prime. In other words, this voltmeter is measuring the voltage across the big R. Okay, uh, what whatever is the reading of the voltmeter measures the amount of potential difference, okay, between point A prime and B prime, or in short, the voltage drop across big R, right? While the ammeter, all right, earlier uh, it was connected somewhere on this part of the circuit to the right. Now it is transferred to the left side, all right? So that is the new positions of the voltmeter and the ammeter. What do you think are the answers to our questions, the voltmeter and the ammeter readings? First, in letter A. All right. So our answer, okay, since voltage across points AB is just equal to the voltage across A prime, B prime, and that the voltmeter is reading the same, okay, voltage as discussed in example 2 earlier, which is 8 volts. All right, so practically the same amount of voltage, because that has been emphasized or overemphasized, that B sub AB is equal to B sub A prime B prime, and that is equal to 8 volts. While the ammeter also still reads the same current of 2 amperes. All right, it is because the current at any point within this path, all right, at any point within this path is the same or constant. So whether you're talking about the current between point B and point B prime, okay, or between A and A prime, the current is just the same, which is 2 amperes. Now, in illustration letter B, notice how the voltmeter this time is connected. All right? Okay, it is connected in series to the whole circuit. In short, it is connected uh, side by side to point B and point B prime. It is located between, okay, point B and B prime. But the best way of describing that is it is in series, okay, to point B as well as to point B prime and to the whole other components of the circuit. So what do you think will be the current, okay, as read by the ammeter, and of course the voltage as read by the voltmeter? So already discussed earlier, okay, and we just want to emphasize this now. The voltmeter, as I mentioned earlier, is so designed so that it's or it has an infinite amount of resistance. Okay, if you remember. And therefore, okay, whatever current is moving around the circuit may not be able to pass through this voltmeter because it has a very, very high resistance. In short, there will be no current in the circuit. All right? So, I is equal to 0. Okay? No amount of current, no amount of charges per unit time can be detected by the ammeter, even if the ammeter has almost zero resistance, but there's nothing, okay, flowing through the ammeter because there is some kind of an obstacle, all right, happening somewhere in the circuit, and that is at this point where the voltmeter is connected. Okay, so it's like the whole circuit has been cut. All right, so no way for the charges to continue to move, okay, and make their complete journey. So that's the effect of connecting the voltmeter in series to the circuit. There will be no voltage reading. Okay, there will be no current either. All right. All right. This is example number 4. Still about uh, the circuit described from examples 1 to 3 so far. Okay. So we now talk about a source with a short circuit using the same battery. Okay. As in the preceding 3 examples, we now replace the 4 ohm resistor, the big R, with a 0 resistance conductor as shown in the figure below. All right. So here's the figure. Again, what are the meter readings in the voltmeter as well as in the ammeter? All right. So earlier, the big R has a certain value, but this time, okay, there's no more resistance or no more resistor. It's equal to 0. In short, it's only a bare conducting wire that's connected, okay, to the battery. All right. And here's the ammeter. Remember, the ammeter is a very, almost 0 resistance. Now that you have provided, okay, a path for current, okay, or for the charges to flow around the circuit freely with no obstacle, no resistance, no opposition whatsoever, okay, it follows that, okay, there will be a current, okay, in this wire, okay, moving through, or for example, from point A and then passing through the ammeter. And such current, okay, can be detected, measured by the ammeter. How much is that current? Okay, so we use Ohm's law, which says that the voltage across AB. All right. So we are describing first the voltmeter reading. Okay. That voltmeter reading can be labeled as V sub AB, and it's equal to the product of current I multiplied by R. All right. And since there is no current through that voltmeter, all right, no current through that voltmeter, it is a very high resistance. Remember, all right, very high resistance, right? So the voltmeter reading will be nothing. It is 0, right? But uh, all the current that is generated by the battery, all right, with nothing to oppose except for the internal resistance, all right? But no external load or resistance that can oppose that current. So we expect a large amount of current in this circuit, and that is measured by the ammeter, right? We just use the formula I is equal to E or epsilon EMF divided by small r. Okay, there is no plus capital R because capital R is 0. So it's only uh, epsilon or EMF divided by the internal resistance of the battery. Okay, that will constitute the current, meaning 12 volts, that's the amount of EMF, divided by the internal resistance of 2 ohms, we get 6 amperes. All right. So this maximum amount of current that a battery can generate, okay, since there is no external resistance available. Okay, we can also put it this way. Okay, even if there's a path or there's a wire connecting the point A and point B, but again, that happens to be of high resistance, so the charges would rather move around, okay, a path with the least resistance, and that is current will or charges will move through this path instead of moving that way, okay, through the voltmeter. There's no way for the current to move through the voltmeter. So it's like the charges are blocked, okay, by the voltmeter. So all the current generated by the battery will be moving only through this path, which is intercepted or measured by the ammeter. So that's how we look at this circuit diagram, the situation. And this kind of situation wherein the current generated by the power source is so large because there is no external resistance to somehow reduce that current. Okay, uh, this is what we call a short circuit. All right, a short circuit. If we're talking about an appliance that has been short circuited, then the idea is the same because there's a wiring that doesn't, I mean that wiring doesn't have any resistance. So the current that's supposed to flow through that particular, for example, appliance, will not pass through that. Instead, they will just take the least resistance route, such as a bare wire with no resistance at all. We call it a short circuit. And I'm sure you are familiar with this hazardous situation, okay, known as short circuit. Okay, in most cases or in most practical situations, such as in car batteries, all right, in car batteries, the internal resistance is so minimal as compared to what we have here in our example. Okay, the small r, the value of the small r is so small, and you can just imagine the amount of current that is generated by the car battery if a short circuit accidentally occurs. Okay, this is an occurrence in such circuit that is not intentional. It happens by accident. All right, and you will be thankful if this won't happen uh, to your what you call this, to your car circuits, because you know what's going to happen. It's possible for the wire uh, to get so hot as a result of not having a resistance. Okay, Ohm's law tells us that the current, okay, for the same amount of voltage, the current is inversely proportional to the resistance. So if the resistance is too small, all right, what happens to the current? It becomes so large to the point that the wire can no longer tolerate such a high amount of current. So there is a possibility for the wire first to get so hot, so intensely hot, all right, and it may in fact burn, all right, and in worst scenario, there's a possibility for the car battery to also explode, and I'm sure nobody wants that to happen. So just be very careful when you are fixing your car battery, all right. Better call somebody who knows how to do it correctly. Okay, so it's better to be sorry, all right, than to have an accident such as an exploding car battery. So this is uh, the effect of having what we call a short circuit. Okay, even in our household electrical circuits, okay, short circuits do happen. Okay, one example of source of a short circuit is using too many appliances connected in parallel. Okay, too many gadgets, appliances connected only in one specific circuit, okay, will cause possibly overloading and short circuit as well, which are fire hazards. So just to be very careful. All right, this is example number 5. We'll be talking about the wattage rating of light bulbs. So you're given two household electric bulbs. Bulb 1 has a wattage rating of 120 watts. Okay, this symbol for wattage, also known as electric power, represents watt. All right, and 1 watt is just actually equal to 1 joule per second. The second bulb has a wattage rating of 60 watts, and both bulbs have the same normal voltage rating of 220 volts. First question is compare the resistance of the two bulbs. Okay. And then the second question, which bulb has the thicker filament? Justify your answer. Okay. So this is what we will do. Okay. We're going to uh, first identify the variables or the data given in the problem. For bulb 1, we say that it has a power, okay, P1 equals 120 watts. And for bulb 2, that is 60 watts. And since the two bulbs are used or connected to the same power source with a voltage of 220 volts, so we say that V1 is equal to V2, 220 volts. Okay, we need to find the amount of resistance, okay, for each bulb, R1 and R2. All right, so there is a formula that goes like this. To find the resistance R, all you have to do is divide the square of the voltage by the given power. So for R1, that's equal to V squared over power P1. Okay? And substituting, we have 220 volts, square that, and then divide this by 120 watts. The result is we will get a resistance R1 which is 403 ohms. Alright? While the resistance for the bulb 2, whose formula is the same, okay, it's just that we use a different value for the power. So the same voltage, 220 volts, square it, divided by 60 watts, and we will get 807 ohms, almost twice. Okay, R1 is just half the value of R2. Now, if those resistances are related, no, such that R2 is almost twice the amount of R1, okay, what do these values for R's tell us about uh, what we call the thickness of the filament, the bulb filament? Remember, in an electric bulb, it is the filament usually made of tungsten. Tungsten that gets so hot without melting, because the melting temperature or melting point of element tungsten is so high. Okay, so without melting, the filament will simply glow, and that explains why a light bulb can produce can produce light, transformation of electrical energy into light. Now, in answering letter B, we just make use of the relation of resistance, big R, to the following, what you call this, properties, okay, or quantities such as the length of the filament and the thickness of the filament expressed as cross-sectional area of the filament. So imagine the filament to have a cylindrical shape, okay, and therefore it has a certain thickness, okay. The area, of course, is just the, how do you get the area of a circle, for example, all right? The cross-sectional area simply means we are getting the area of that circle, no? That describes the cylindrical shape of the filament. So it is pi r squared, correct? The greater the radius, okay, of that filament, the thicker it is, and therefore the greater the cross-sectional area. All right, but it is the thickness or the area that we are trying to compare. Okay, uh, compare the area or thickness to the resistance of the bulb. All right, and since earlier we got in letter A that the resistance R2 is higher compared to R1, assuming the length of the two filaments, okay, the lengths are the same, and they are made of the same kind of material. For example, both are made of tungsten, okay, whose what we call resistivity constant. This Greek letter rho stands for resistivity. It's like the opposite of conductivity. All right. So the resistivity value, conceptually, it tells you the ability of a given material to oppose, all right, to oppose the flow of charge. So that is what we call resistivity. So assuming that is constant and the length of the filaments are constant, so we are only relating the thickness in terms of the cross-sectional area to the resistance, okay, we say that the bulb with the smaller resistance has the thicker filament, and that is bulb 1. We are down to our last question. Factors affecting power. The problem is Robert and Princess are discussing whether an electric heater with a large or with a small resistance will yield the greater heat output. Robert favors a small value of R because he says power is equal to V squared over R. Princess favors a large value of R because, according to her, P is equal to I squared times R. Now, what is your own conclusion? Okay, so let us first clarify some terms here. When you say greater heat output, we actually mean the uh, the amount of uh, energy, okay, that is transformed in using electric heater. Of course, we are uh, producing heat or thermal energy, okay, is being produced by a heater, okay, with the use of electric energy. Okay, or electrical energy is being converted to thermal energy. All right, and uh, according to uh, Robert, a small value of R, meaning the resistance of a heater, okay, the small value of resistance of the heater is what can produce the greater heat output, because he is using this formula for power, All right. Okay, so according to this formula, at a glance, tells you that P is inversely proportional to R. So that's the reason why Robert thinks that the smaller the value of R, the greater the amount of heat produced per unit time. All right, power. While Princess, okay, favors a large value for R because of her belief that the power is equal to I squared times R, and that using this example or equation, okay, it looks like R is directly proportional to the power. So that the bigger the value of R, the bigger the power. So which between these two students, okay, is correct. All right, so again, we will identify the given data. Okay, for heater number one, which is uh, the heater used by Robert. Okay, the given R, for example, is 1 ohm. Okay, there is a need for us to assume certain values for the resistance, and for simplicity, we choose a value that is a small value, such as 1 ohm. And that for heater number 2, the resistance R2 is equal to 2 ohms. Okay? Now, uh, as we all probably know, okay, these heaters will be used, okay, using our household voltage supply. Our household voltage supply, for example, okay, in the Philippines, we are using 220 volts. All right? But in other places, probably they are using 120 volts or probably 110. Okay, it depends on the country. All right, but for simplicity, once again, we just choose a small value for the voltage, V1 and V2 being equal. Let's say it is equal to 20 volts. And we are going to calculate for the power, okay, P1 as well as P2, using both equations mentioned by Robert and Princess. So here we go. Okay, as claimed by Robert, P1 is equal to V squared over R1. Okay, and substituting the given voltage and R1, we get this power P1 of 400 watts. While, okay, for the higher resistance heater, okay, we get, using the same formula, we get 200 watts. And obviously, okay, obviously, it looks like that Robert's claim is correct, okay, because the heater with the small value of R, all right, has the greater power output, okay. That is the result of Robert's computation here. Let's look at Princess solution. Okay, for Princess, she uses the formula P1 or power is equal to I squared times the resistance. And using the two given values for the resistance, R1 and R2, okay, the first heater also produces the same power of 400 watts, the same as what Robert's formula, okay, yielded. That's also true for the second heater, okay. The same power output was produced, 200 watts. But, again, who between them, between Robert and Princess, is actually correct? Okay? P1 refers to the heater, okay, with the lower resistance, while P2 refers to the heater, okay, with the higher resistance. So, according to Robert, the small value of R, okay, will yield the greater heat output, while Princess claimed that the larger value of R okay, will yield the greater heat output. So, who between the two uh, students is correct? Of course, it is Robert. You know what the scientific basis can be cited why Robert's claim is correct? All right. It is the fact that both heaters, okay, will be connected to the same power supply whose voltage is the same, okay, such as what we use here, 20 volts. So, in his equation, Robert's equation, that power is equal to V squared over R, okay, he is correct in saying that a small value of R, okay, will produce the greater power because uh, the voltage here is held constant. All right. V2 is constant, and therefore it is correct to say that the smaller the value of R, the greater is the power output. Okay. Whereas in Prince's equation, okay, the current I is not constant. Okay. The current I is not constant. In fact, if you notice in her substitution of the given, okay, it can be computed that the current for a given voltage of 20 volts and for a given resistance of 1 ohm, okay, the current in fact is 20 amperes. All right. But for the higher resistance of 2 ohms, okay, with a given voltage of 20 volts, okay, the corresponding current in fact is lower. So, it is not correct to say, using Prince's formula, that the greater the value of R, okay, the greater the value of output power is. That is not quite correct because that's only true if the current or I squared is constant. And that explains why Robert is the one that is correct. Thank you very much. Okay, that ends our uh, tutorial and hope to see you in my future video tutorials.